So the last day we introduced it, and we're going to continue with that today. The last day we looked at a very simple example where we just looked at a sine curve or sine wave and we amplified it. And what we did was we set a parameter from within MATLAB that will be used in Simulink, which essentially was the gain of the amplification. So we pulled an old sine wave from the block, put it through a gain, and then outputted it to the scope. And what we did was, this is the Simulink model, but this is an amplifier that has a certain parameter called gain. And what we did was we showed how, at least I think we did this, we showed how you can set the gain from either in the MATLAB base workspace. So when you run the model, you have a variable called gain in here, and the model will look for that value. And the first place it will look for it will actually be in the model workspace. And if it doesn't find it there, it'll look for it in the MATLAB base workspace. So, in other words, when you're running your models, you can set parameters from either in the base workspace, or as we see for more complex models, what you do is you associate a script with the model that will generate these parameters. So, this is where we are. You're right or my right? Okay. Okay. So there's the model. Actually, the variable is called sine. No, that's the signal. Yeah. There is the variable. Okay. So there's two ways you can actually set that. As I said, you can set it from the base workspace, which I have done here somewhere. There you go there. Alright, so this is the base workspace, and as you can see I define the value of gain sine being 6 here. And then when I run the model, it finds it, and sure enough, the gain is 6. Right? Alternatively, what you can do, which is what we'll be doing more often than not, is where you're defining a whole load of parameters that are really for the model. What you do is you write a script that you're familiar with, and then you say every time you run the model, make sure you run the script first. And the script in this case, of course, is just setting a single parameter, but as you'll see in future models, it will do a hell of a lot more. So what we're saying is, when you run this model, I want to run this script first. And how you do that is you go to the model workspace. So if you look at the model explorer, there's the base workspace, here's the model, and you can click on the model workspace, and you can see model properties here. You've got callbacks, which is a preload function. So what you're saying is, before you load the model, run this script. And you set the name of the script there. So then when you run that, when you run the model, it will look for that script somewhere, it finds it, it sets the parameter, and off it goes. Okay, so that's the two ways of doing things. But remember, by default, it will look in the model workspace first. So for example, if you ran that model now, and you went back into the base workspace, and set gain sine as 146, and you run the model, it won't make any difference, because it has found the value in the model workspace. That's the first place it will go to search. Okay. All right. That was that. Right, so I want to move on to doing a few other bits and pieces. In terms of getting your head around Simulink, because you know, it's a little bit different. I know MATLAB is a bit different, but Simulink is also quite a bit different. And actually, these notes are a bit different from what's on Blackboard. So, importing data into the model from MATLAB. Well, we've seen it already with gain, but obviously gain was a single parameter, so it was a scalar value. The value was 6 and the value was 12. And in this model, there were varying inputs, and the varying input here was defined by a block, which was a sine wave that we pulled from the library browser. But let's say you want to set a parameter in the model that varies with time. So you have a time varying input. So remember, a model runs a system over a period of time. And what you want to do is you want to specify one of the input variables that happens to change with time. So you do that using the configuration parameters dialog box, which is shown somewhere here. So here's our model here. Instead of the sine wave, what I'm doing is I want to read in data. So this is an input block from the sources library in Simulink. So by pulling over that block, you're saying, I'm going to read in data somewhere. But then it's up to you to specify what that data is. So in other words, the input to the gain block will not be a sine wave block. It will be some data that I configure. And the model runs over a period of time. So what you need to do is you need to specify how this input signal will vary with time. So you're giving the model what it needs. You're giving it how the input signal varies with time. So if you want to specify how an input signal varies with time, how many vectors do you need to give the model? 2. One will be time, and the other will be the value of the input at that time. Okay? So, the input must be an array or a structure. We won't be coming anywhere near that. So you specify the input. Time must be first, and then the input signal at each time iteration is given by you in this case. It can't be anything, of course. So t is the time vector. It must be column format. As you know, I've tended to stick with column formats, and I didn't need to. So when we were doing curve fitting, I could have used row format, but I didn't. And the reason is it's better idea to use column format because you run into problems here with row formats. So t is the time vector, and then u is the input variable at the corresponding time. By default, simulation time and the model outputs are saved to the MATLAB-based workspace. So this is the what we're trying to do. So ultimately, in the configuration parameters, you see this data import and export. So you need to specify the names of the input data. So in our case, we have a vector called t, which is time, not surprisingly. And then we have an input vector called vector. Well, maybe I should call it something else. But it's just the data at each time. And t must be first. Okay. And in this case, I'm saying, well, what do I want in the workspace? So when you run the model, by default, Simulink will throw stuff out into the base workspace. Why? So that you can use it then. You can maybe plot it, or you can file it somewhere else, whatever you're doing with your model. And by default, it gives you time. So if you want to specify something else, click on that box there. So, before we run the model, so when we run this model, essentially, Simulink will look for a variable called t and another variable called vector. Right? So it looks for them, which means you need to specify them first. So as you can see down here, I specify the time, 0 to 25, and I specify another input, which is linear, really. So in other words, as time increases, so does, that's t, and and that's vector. They both go to 25. Alright? So it's just a very simple linear input. So we're getting rid of the sine wave and we're just putting in something like this as the input into the game. Alright, so we specified them now. Then you can run the model and sure enough you get this. So we're getting the output as well because we have specified the output here. So we're getting T out and Y out being saved to the workspace. There's T out, there's Y out, and there's the inputs, T and vector. Alright? Okay. Any questions? And one thing just to recall here, because we haven't really focused that much on it yet. Here's time, which is 0 to 25, so it's 26 by 1. Here's T out. So T out is 51. Why is it 51? Sorry? Why does it take every half? So in other words, sorry? Well, remember the sinusoid is gone now. So essentially our input is literally a straight line, which goes from 0 to 25 in time and 0 to 25 in input. But when MATLAB is running this model, what it takes, because remember a model, what's a model? It runs a system. Now what MATLAB is doing is it's running it at certain points, right? It doesn't run it at an infinity of points, because how many time points are there between 0 and 25 seconds? There's an infinity of them. Depends on the granularity you want. So what Simulink does by default is it looks at the length of the time vector and it divides it by 50. It's a very crude approach. So that's why there are 51 data points in the output. So you specify you want the model to run for 25 seconds, but you don't specify how often you want it to run over that 25 seconds. MATLAB does that for you, or Simulink does that for you. And the default value is it divides the timeline by 50, which gives us a half. Okay? So this is the actual intervals with which Simulink runs the model. So it runs the model essentially 51 times, iterates 51 times, and these are the outputs at each of those iterations. So needless to say, the gain is 7. Okay, so that's why we get Y out is 7 when the input is 1. Sorry, no, it's not right. Is that right? Yeah, that's right. Alright, one thing you might notice here are these strange icons there. And essentially what that is in Simulink, which is a really good tool, it allows you to look at stuff, look at different signals throughout your model. Now by default I've stuck in a scope here. So when you double click on a scope you get an output which will be just whatever the gain of the input signal is. But if you want to look at how the model is working right throughout, you stick in these what are called signal viewers. And what you do is you select signals and right click on them, and it allows you to create and connect a viewer. Now with MATLAB and Simulink, of course, there are millions of options, but the one to choose is go to scope. Not floating scope, just use scope. Don't ask me why, I can't remember the details, but there are differences that will do your head in. So just stick with scope, and by doing that, you select one of them, and then what you can do is you can select another signal and attach it to the same scope. So what it means is that as you're running your models, you can very quickly get a view as to what's happening throughout the model. So you can see in this case, what you see here is not this scope, it's essentially these two here. Actually, this is an older version of Simulink, that's why it was shown as a pair of glasses here, that you were looking in at a signal. It's been since changed to this icon here. But regardless, this is what you'll see. So you can see we have the input signal and the output test signal. And here you have input signal and output test signal. Actually, there is something unusual there that I just noticed in terms of the timeline. Can anyone tell me what it is? Yeah. I must have been messing around with that. Remember the input here goes to 25. So, but actually what I'm showing you here, it must have been when I was messing around with it. It's actually gone up to 100 there in terms of the input. So just be careful about that. So, okay. So in terms of messing around with those signal viewers, I've just shown you two different options here. And this is the icon there for changing the parameters for the viewer. You can select the number of axes. Here we have two axes. So in other words, the two different signals are shown on separate axes. And we include legends on both. Down here you can see I've reduced the number of axes to 1. So both signals are shown on the same axis. So it reminds me a bit like of Word and Excel Simulink. Now that might turn a lot of people off, and indeed I can see why. In that it has so many options. So you can spend your life going through the options here, but the most important ones that I've always found are auto scale, which is that one. A lot of the time your signals will disappear. And they're disappearing because you're focusing in on a certain part of the output. If you press auto scale, it will automatically fit everything into what you see. That's probably the most important one. And then this one here for selecting the number of viewers. Okay. Alright. Another thing you can do with Simulink is to model a decision statement. Now, rather than looking at the logic behind that, just look at it in a visual display. So this is essentially an if-else statement in Simulink. So you can imagine you're modeling a dynamic system. Whether it's an ABS system in a car, and every now and then you need to model, well, what will happen if something happens? So how do you model that? How do you build that into the logic? Using Simulink. So what we have here is essentially a switch block, and it has 3 inputs. And essentially, depending on this input here, you will select either this one or this one. So if you were to write pseudocode for that, this is what you'd have. So input 1 is the defining input. It's the one that dictates whether you select the top or the bottom as your output. So if input 1 is greater than or equal to 0, then you select output 1 becomes 3. In other words, the top one. Else output 1 becomes minus 3, the bottom one. So if the input signal is positive or equal to 0, you select this. Else you select this. So as you can see, I've set up a sine wave here. And here's our sine wave. So whenever the input is either equal to or greater than 0, then the output is switched to here, which has a constant value of plus 3. So that's why you see plus 3 immediately switches to minus 3 here once the input dips below 0. So in other words, you're creating, I suppose, a square wave from a sine wave. But it's not something we use that much, a switch, or at least any of the assignments I've said so far, you don't need it. But you know, it's something that can be quite useful in Simulink as well. The threshold here, this bit here, it says greater than or equal to 0. That's defined, and if you click on that block, you'll see this threshold here, and the criteria is here. So if the central input is greater than or equal to a threshold, and you set the threshold here as a value of 0. So again, these are commonly used blocks. that can be very useful. Simply. Okay, one thing we will definitely be using quite a lot from now on are integrators. So this is a simple model, and what it does is it has an input, which is a pulse generator, and we have a multiplexer here that just shows both signals. So it'll show the input and it'll show the output, and the output is just the integral of the pulse. So the symbol for an integrator is 1 over s, and we're running over 30 seconds. So this is what you see. Okay. So how does that work? Well, if you click on the pulse integrator, again you said its parameters, and its parameters are here. Its amplitude is 1. Its period is 5. So every 5 seconds we get a pulse. The pulse has amplitude 1, and the pulse has duration 20%. So 20% of the period. So 20% of the period is 1. So it's of amplitude 1 and duration 1. And then it shuts down and starts again. So you can specify the characteristics of your pulse. And of course, all we're doing then is we're feeding that in and we're integrating it. And of course, integration is just getting the area under that pulse. So sure enough, you can see in purple here, the area is linearly increasing until it reaches this point. And once the input signal drops to 0, we no longer get any more data. So nothing more to integrate. And then it starts again. So you get the output there. And again, I'm selecting them both on the one output there. One thing to be aware of too is the integrator. This block here, if you click on that block, the one important parameter you need to set is the initial value. So the initial value here is 0. So, in other words, the integrator starts off with a value of 0 and integrates from there. There's a different pulse. So you can see this has an amplitude 1, a period of 2, and a pulse with a 50%. So you get a very different pulse characteristics, and obviously you get a very different integral as well. And then finally, here I have changed the integrator initial value. So if you click on the integrator block, as I said, one of the key parameters you need to set is the initial condition. So in this case, I've set the initial condition to 5. So what happens essentially is it starts from 5. Alright, now we'll see that. Can anyone think, you might think, why in God's name are we covering this at 9:45 on a Monday morning? But where have we seen this already? In the models we've covered, where might it be important to have an initial value for an integrator? Perhaps, or even, no, the models, in fact, what models have we looked at in class here? What's the biggest model we're going to be covering? Well, that's one of them, yeah. Not the biggest one, though. Sorry? No, they're actually quite easy ones to model. The house, yeah. So the initial temperature of the house. So, we've got a house. You'll all be building your house in a few weeks' time, and you have to figure out how much it costs to heat it. And remember, you put energy into a house via your heater. Your house loses energy through the walls and windows, and if there's a net gain, the temperature will go up. But of course, you have to set the initial temperature for the house when your model starts. If you don't set an initial temperature, it will default to 0, which means you're starting your house from 0, which is a cold house. So that's just something to be aware of. Okay, that's one, I suppose, tangible area or a tangible example of where you need to set your integrator initial condition. Okay, Simulink is full of very good demos and very good help files as well. And there are actually videos as well. Have any of you looked at any of the videos yet on how to use MATLAB and Simulink? Particularly Simulink. There's some really nice videos on working your way through it. So, a bouncing ball. This is the one that we'll be building ourselves, and there's lots of other really interesting stuff, I suppose, particularly from an engineering perspective. Very simply, I mean, you can build a simulation of a bouncing ball in about 3 minutes, and you can change the damping, you can change the height. I mean, it's a really, for the engineers who've done their dynamics, system dynamics, it's actually a fantastic tool for actually seeing what will happen when you change the modeling parameters. Okay. All right. So it's time to start building our house. So it's the first main model that we'll work on over the next week or two. But before we do, we need to cover kind of the basics of thermodynamics, which I know that all the engineers are doing thermodynamics at the moment, isn't that right? So for the IT guys, I just need to cover some of the basics really, as much as you need, and it is kind of intuitive, I hope, at this stage. So we covered some of it last year in first year. Okay. So, as you know at this stage, we've covered it a couple of times, we're going to develop a building model. We're going to model the physical structure. We're going to model the heater. We're going to model the external temperature and the desired input temperature. And we're going to model energy costs. Alright? So that's the overall structure of what we're going to be doing. This is not the Simulink model, this is my own model, which is the very same really, except we talk Celsius over here rather than Fahrenheit. So there's no need for Fahrenheit to Celsius converters, which you might have seen in the initial models. So the Simulink model works in Fahrenheit, and it also reads in a sinusoid. It models the output temperature as a sinusoid, which is, not a bad model as things go. For my model here, we're reading in data from the workspace. So as we've shown earlier, so I'm reading in the temperature data, actually, usually it's from the weather station upstairs. So when you build your model, I will give you a month's data from a weather station we have on campus. So what you'll be doing is you'll be using NUIG weather for your house to figure out how much it will cost to heat it for a month, or whatever. Okay, so that's what we're working towards, alright? But as I said, before we do, I just want to cover a bit of thermodynamics. So a couple of terms you're going to have to come to terms with. We have conductivity, which is known as K, but is actually also known as U. So who here has not heard of a U value? That's good. So what is a U value? Just to see, is there anyone awake? What's a U value? You an engineer or IT? IT. Still though, what's a U value?
It's like how easily it passes through a substance.
The higher the U value, good or bad?
I know.
Oh, they're talking to you. Bad, yes, Dave, you're right. Okay. So the U value is how much energy, how much heat is lost mobility per meter squared per degree differential. Right? So high U values are bad news if you're trying to keep your house warm. Thermal resistance is literally the inverse of U, as you see. So what it is really is how resistant is my house to losing heat? Heat flux is essentially the rate with which energy is moving in either direction. And of course temperature. Well, the models typically work in Kelvin, which can be a bit confusing because we have uppercase K for Kelvin and we have lowercase k for conductivity. So actually, I think in some of my slides, PowerPoint did its best to confuse you. So it just flips between lowercase and uppercase. So just keep an eye for that. Hopefully you'll understand what the context which is meant. But anyways, be careful of that. Okay, so Kelvin is capital K, which, as you know, is a kind of a similar model to, a similar scale to Celsius, except for the starting point. Okay, so small k, make sure that's small k in your slides. Small k is conductivity, it's the ability to conduct heat. What is heat? Energy transferred from a high temperature to a lower temperature system. So it's defined per unit area. So I just want to make sure you get the units right, because they can be a bit confusing, and I'm an absolute stickler when it comes to units. So I want to make sure you guys get your units right. Okay? So maybe this is an easier way of looking at it. So here I have a block of material. And the block is 1 meter by 1 meter by 1 meter. It's a cube. So the conductivity, small k, is watts. What's a watt?
1 joule to 1.
Sorry?
1 joule to 1.
Joule per second.
Yeah.
Okay? So watts is how many joules of energy per second. So the conductivity is the number of joules per second per meter thickness of a material. So the material is a meter thick. Just imagine a meter thick of material, but it's defined for 1 meter squared of that material per degree Kelvin, right? So in other words, we have a temperature on one side of the block, and we have a temperature behind the block. And the conductivity is the number of joules per second that come through that 1 meter thick block for every meter squared of material for every degree Kelvin difference. Now obviously if there's 0 degrees Kelvin difference, nothing will happen. But once there is a degree Kelvin difference, you will get a tendency for energy to flow, and that the amount by which it will flow is defined by the conductivity. So in other words, metal will have a much higher conductivity than fiberglass. Now U values are really similar, except when we talk about U values, we talk about the U value of this, right? And the U value, again, is given per meter squared. So we have a meter squared of this piece of timber, but of course this piece of timber is not a meter thick. Typically it's this thick, or typically your insulation in your roof might be this thick, or maybe this thick, or this thick. So U values are defined for a certain physical type of structure. So in our case we have a meter by meter area, and we have a certain thickness, which in this case is, for example, a centimeter. So it's a tiny piece of material. So the U value is how many watts per meter squared per degree Kelvin. And in fact, the relationship between them is just the thickness. Here it's a meter, and here it's, in this case, it's a centimeter. And in fact, the U value is the conductivity divided by the thickness in meters. So in other words, if you have this block of material, and then instead of having a meter thick of it, let's say you've only 1 centimeter thick. Will more heat or less heat go through it? Intuitively, if you reduce the thickness from 1 meter to 1 centimeter, more. So if it's 100 times thinner, the U value will be 100 times the conductivity. Alright?